In simpler language, the kernel of a linear transformation is the set of all vectors that you were able to undergo the identified transformation that will allow the result be equal to zero vector. So in short, we're just going to list all of them or find the values of the components which could make the transformation equal to zero. This is also true for this here. Since we have in these two linear transformations, we have the transformation of vectors that are element of R2. We are expecting as well that our set of vectors here are also in R2. So how do we show this process? Our process here is to make sure that again this entire form here will become zero vector. Again, our zero vector here is in R2 0 0. Hence we're going to solve for the components x and y respectively. So to do this, we simply take here, copy the notation. It must be equal to x plus 2y, then y minus x here. Again, this entire form will be equal to 0 0. Okay, so we have 0 and 0 here. So that would mean, let me rewrite this here again. We have x plus 2y and y minus x must be equal to your 0 vector 0 0. And let's try to determine the possible values of x and y variables. So equate them. We have here x plus 2y equal to 0 and y minus x is equal to 0 here as well. Now to solve for this, there are a lot of processes. You could even use here matrix form, augmented matrix, and even the row echelon form of the matrix. But since we have x and x here, let me just use the elimination method. Cancel that out. I have here 3y is equal to 0, so y is equal to 0. With that being said, here in any of this equation, let's have x plus 2y equal to 0. So x plus 2 times 0 is 0. So x is also 0. In short, the components of x, our vector, we have here x and y. In this case, we are going to say that just for the purpose, we have here x and y here. So we have x and y are both 0. So the vector, we only have one vector that will create a 0 vector as a result of a linear transformation is a vector 0 0. And our kernel of t would be a set containing the said vector. This is for our first item. Now for our second item here, duplicating the process, we will have here transformation of x and y is equal to x minus y, y minus x, and that equivalence should be equal to a 0 vector. Still 0 0 because we are in R2. So our equations, x minus y is 0, y minus x is 0. Again, let's just simply use here, of course, we cannot use here elimination method because we have 0 both sides. We have negative, negative, positive, negative. Okay, what we can do here is we can use here the augmented matrix. We have 1, negative 1. We have also here. So by doing that, we have our x is negative 1 and 1 here as well. Okay? So if we're going to add row 1 plus row 2 to have a new row 2, this is what will happen here. So this is 1, negative 1. Of course, this is 0. This is 0 here as well. So in short, we have the equation x minus y be equal to 0. Okay? In this case, since we have two variables now, we can let y be t. That would mean x minus t is 0. X is also equal to t. In short, there are infinitely many possible values here for our x and y components for our vector v, x and y, as long as they are of the same. Okay? So we can have it here. We have t and t, or much better in a set, you have here t, okay, such that your t is an element of R. So any value of t as long as we have the same components here. So if say for example 2 and 2, 2 minus 2, 2 minus 2, 0. Okay? Negative 1, negative 1. Negative 1 minus negative 1, that's plus 1, 0. Same thing here as well. This is our kernel, okay, of t for our second given. See that the process are different because earlier it's very exact. Okay, even we use the elimination method, but here we don't have exact values, so we use here the row echelon form and came up with this representation. So we have these two different, okay, kernels of t. By the way, we have parentheses here. So this is how we show the kernel of a linear transformation. Thank you very much for watching.